All right.
Yeah, can you see my screen?
Yep, it's good. Okay, let's
Good.
start. All right. All right. Welcome everybody. It's our pleasure to have with us Wang Peng. Wang Peng is a postdoctoral scholar at the University of Michigan. He's working with Laura Bolzano and Qing Su. Uh, Before this, Wang Peng got his PhD in systems engineering and engineering management from the City University of Hong Kong. Um, Lots of interest in data science. He works, you find it works on topics in intersection of optimization, machine learning, data science, and I think these ideas of low randomness and sparsity will seem to be a common theme in his work, and I think you see quite a lot of this today as well. It's a pleasure to have you here, Wang Peng. The floor is yours.
Yes, sure. Thanks. Yeah, thanks for the nice introduction. Well, today I will present my recent work on diffusion models. That is to understand distribution learning of diffusion models, low dimension modeling. This is a joint work with my collaborators from the University of Michigan, uh, including some students and also my supervisor there. Before I get started, I will briefly overview the history of generative artificial intelligence. Over the past 10 years, generative AI has achieved great success, especially in empirical side, right? Some powerful models and also very useful products have been proposed. Some typical example like the biracial encoder, generative adversarial networks, transformer BERT clip these models, and built on these models. Some useful products like the ChatGPT, Sora, these products have been released by some high-tech companies. Although we have achieved great empirical success, our theoretical understanding on this model is still very limited. This is because most of these models are built on deep neural networks with very complicated architectures. And we don't know what happens at the inside layers. We usually treat this neural network as black box to use them and training them. So in this work, we focus on a special instance of generative AI models, that is the diffusion model, and we try to provide some theoretical understanding into these models. In general, the task of generative AI models can be formulated as follows. That is to learn the underlying data distribution from training samples. Like here, we plot some figure. You can see we have a training sample. We have some training sample denoted as xi, and we assume that the ID sampled from the underlying data distribution, we denote as p data. Like here, we have some cat images, right? And maybe in other tasks, the training data are some audio or text. And then based on this training model, based on this training samples, we use a neural network based generative AI models to train a neural network and to learn the underlying data distribution from these training samples. In the literature, there are two main approaches. The first approach is the direct approach. That is to use a neural network. We denote the p theta to approximate the underlying distribution with the maximum likelihood approach. This is a direct approach, just to direct to learn the underlying data distribution using neural network. And another approach in the literature is an implicit approach. Instead of learning the underlying data distribution, we aim to learn the gradient of the log density of data distribution. That here you can see we use a neural network parameterized by theta to learn this, to approximate this score function. In literature, we usually call this one the gradient of log density of of the underlying data distribution as the score function. And so this approach in the literature is also named the score matching. And this is an implicit approach. So based on this learned distribution, then we can use them to generate some new samples from the learned based on the learned model. Like here, use the learned distribution, we can get some new cat images, right? And usually, in practice, we help the learned distribution is close to the underlying data distribution. Yeah, that is a general task of that is the basic task of general models. Well, in the literature, there are some two typical examples of this general model. The first one is variation autoencoder. I think many audience here may know about this. And it consists of encoder and decoder. However, variation autoencoder usually suffers from the poor generation quality because like here, we have some input images, right? And after training, we use the variation encoder to generate new images. And you can see here, the image quality is get worse, right? Compared to the images, original images. And the second typical example is the generative adversary network. It's proposed about 11 years ago. And in general, this model consists of generative network and discriminative network. And this model is not so stable to train in practice, especially on large-scale large-scale data sets. Because when we use the GAN, we need to solve a min-max problem. And we use some grid in practice, we use some algorithm like the grid descent ascent, and usually may diverge, sometimes may diverge. And so that is why it's not so stable to train it. Well, so recently researchers proposed to study the diffusion model. Diffusion model can address these two issues. Like here, the image, the generation, the quality of the image generated by diffusion models the quality is very high. And in training, since diffusion model training loss is just a minimization problem, it's very stable to train. And I will specify the training loss later. And here I just list some typical applications of diffusion models, like the DALI model. We can use diffusion model to input some text and generate some images based on the text. And also like use diffusion model to do the inverse, to solve inverse problems. And also like the control net, right? This is the ISSW, the best paper 2 years ago. Here, like here, use control net. With the input is just some sketch of image, and we also input a text prompt, and then based on this prompt, we can use diffusion model to generate the images with fine-grained details. Well, then I will specifically introduce diffusion models, use some mathematical equations. In general, diffusion model consists of a forward diffusion process and a backward denoise process. Like we have a clean image data, right? Denoted as 0. It may generate by some sampled from some underlying data distribution. In the forward process, we gradually add the noise. You can see here until it becomes like a fully corrupted image. And then in the reverse process, suppose that we have learned the score function of the data distribution, then we can use this score function to do denoising and then generate some new images. Like you can see here, we visualize with some animation to visualize the reverse process of diffusion models. You can see started from some noise. We gradually remove the noise, then generate different images. Okay, so now I will use some introduce some mathematical equations to characterize the diffusion model, the forward process and also backward process. You can see here in the forward process, we gradually add the Gaussian noise to an image sample from the online data distribution, and this process can be characterized by the following stochastic differential equation. That is this one, this stochastic differential equation. And here, the f and g are predefined diffusion and drift functions. They are used to control the noise schedule. And WT here are standard window process. So suppose that we denote the probability density function of xt as ptx, denoted the probability, just later we call PDF, denoted this one, the PDF as ptx, right? Then based on this forward SD, we can explicitly write this probability density function as follows. That is conditional on this x0. The ST, the PDF, takes this form. That is the multivariant Gaussian with mean STX0 and covariances, ST square, sigma t square times an identity. And here, ST and sigma t, these two scalars are dependent on these two functions, predefined diffusion and drift functions, that these forms. Okay. Any questions about the forward process? If not, we go ahead. Similarly, we can also use a stochastic differential equation to characterize the backward process. You can see here. That is this stochastic differential equation. And here, the ft and gt we have defined here, right? That just some diffusion and drift functions, this f and gt. And this one is a score function. Here, we suppose is null, right? In this here, that is, this is a score function. And omega w bar t here is another standard window process independent of this window process. So it has been shown in the literature, if this score function is null, suppose it's given, the backward process can recover the theme distribution as forward process. That means we can use this score function, we can generate the new samples, use this reverse process from the underlying data distribution, right? However, in practice, this score function is unknown because like in applications, we have some data set, and this data set just are training samples from the underlying data distribution, like the ImageNet, CIFAR10, this data set, right? They are just some training samples instead of the underlying data distribution. So this P data is unknown. What we have just some training samples. So to use this reverse process to generate new samples, we need to learn this score function, right? So the remaining task is to consider how to learn the score function. Well, in the literature, actually, the approach is very straightforward. We just use a neural network parameterized by theta. We denote as theta, this neural network, and the input at different time is at different time t is xt. The input is xt, and usually in the literature there are two standard neural network architectures to parameterize this score function. The first approach is UNet, this architecture. You can see here like this one. And another one is a transformer. And this is also very popular neural network architectures in like many applications of computer vision and also natural language processing, right? And actually it turns out it works very well also in the diffusion model applications. And then based on this network architecture, this network parameterization, then the next question is how to learn the network parameters theta, right? How to learn this one. And in the literature, the approach is we just need to minimize the following training loss. That this one, you can see here the training loss is to do what? That is to minimize the distance, the L2 distance. This is the L2 distance between the output of this neural network at different time t and the corresponding score function, the conditional score function. You can see here we take an integration over the underlying data distribution and also the time t and also the xt, right? Note that this actually is this is essentially a population loss because it's integration over the underlying data distribution. But in practice, we only have some empirical samples, right? That is a multi-delta, that is empirical distribution of this sample over the training sample from this underlying data distribution. So in practice, we will replace this underlying distribution by the use the empirical distribution that use in practice we use empirical loss. So to optimize this theta, in practice we just use some training samples from this underlying data distribution and also some sample time t from 0 to 1 and some noise from this standard Gaussian distribution, right? And then compute the stochastic gradient descent, then run the stochastic gradient descent to optimize this loss function. Okay, any questions? If not, we go ahead. That is just the basic setup of diffusion model, the forward process, the backward process, and also the training loss. So in this work, we try to demystify some mysteries behind the success of diffusion models. The first interesting question we want to study is the generalizability of diffusion model. Because in practice, also in our some experiments, we observed that diffusion models escape the transition from memorization regime to generalization regime. That is, sometimes diffusion model just generate images that already exist in the training data sets. But sometimes diffusion model can generate new images that never exist in the training data sets. So we want to understand when and why diffusion models generate new samples. And the second question we are interested in, that is control and manipulate the generated contents of diffusion models. Yeah, since now many researchers care about to achieve the controllable generation. And in this talk, I will mainly focus on these two questions. And okay, and then to answer these questions and also analyze the diffusion models to do some theory, we also may match. Yes, any question? Go ahead. Seems not.
It does not seem that there is a question, so
okay.
Yeah.
Let's go on.
Yes. So in this work, our main goal is to, based on these two questions, our main goal is to improve the interpretability and the controllability of diffusion models. But when we want to achieve this goal, we may meet some fundamental challenges. The first typical one, that is usually the neural network we use in practice, especially in applications, is highly parameterized, right? And it's also like black box, not easy to figure out what happens at the inside layers. And the second one, that is the training loss I just show in the previous slides, is usually highly non-convex, and its landscape may be very complicated. And the last challenge is about the data sets. Like in practice, we use ImageNet, right? So for turns, these data sets, they're usually very high dimensional and massive, and the underlying data distribution is not accessible. And another bad news is from the literature is usually use diffusion model to do density estimation. It suffers from the curse dimensionality. That means to learn absolute accurate score function, the size of training samples usually grow at this order. That is epsilon to minus n's power, and this n is ambient dimension. Like this example, like in Silver 10 dataset, right? The ambient dimension is about 3,000. Like if I want to train a diffusion model to learn like 0.1 absolute accurate diffusion, the score function, then we need about 10 to 3,000 power. The training samples is incredibly large. In practice, of course we don't have so many training samples, right? But we can still, like in application, we can still observe the trained diffusion model seems can learn the underlying data distribution, right? It can generate some new samples and meaningful samples trained on this finite number of training samples. Okay, here are some main references for this talk. That is the first one, our recent conference submission, and it's a joint work with my collaborator in the University of Michigan. And the latest read, our last year, some conference publications like in SML and in Europe's, these conference publications. Okay, so later, first I will talk about very interesting phenomenon we observed when we train diffusion models, that is memorization and generalization. So before I talk about it, I need to mention how we measure the memorization and the generalization. Here in our experiment, we use a following metric, that is the self-supervised copy detection similarity, this metric. And this metric actually is very simple. We use a neural network, that is this one, the neural SSCD, this neural network, to extract the main content from these two images. Like here, we have two images. We focus on this figure here. We have the image X1. We use this neural network SSCD, this neural, the convolution, this CNN neural network, and we also denote that H. Use this one to extract the main content from this image that is mapped from the image space to some future space, and then we get a vector, the future vector HX1, right? And then for the second image, we do the same thing. We apply the same procedure and get the feature vector hx2. Next, what we to do is compute the cosine similarity between these two feature vectors. Obviously, this cosine similarity should range from -1 to 1, right? So if it's close to 1, that means this similarity. If the similarity is close to 1, that means these two images, x1 and x2, are very, very close to each other in terms of the feature content. And if it is like close to -1, that means these two figures are very different. Okay, so based on this metric, the MSSAT, this similarity, we can further define the generalization score. You can see here we have some training samples denoted as yi. We have n training samples, and we also train a diffusion model and generate m samples, generate m images denoted as xj, these images, right? Then we can further define the generalization score as follows. Let's take a close look at what's the meaning of this equation, these definitions. You can see here, this summation is over the indicator function. This is indicator function. And in the indicator function, that is to maximize over the MSSAT, this similarity. You can see, given generated images, xj, given this one, we want to find the image in the training data, yi, right? They're such that their similarity, the max over all the images, the similarity is larger than 0.6. If it is, if we can find one, then the indicator function is 1, and otherwise this indicator function is 0. So in some sense, this indicator function that is to want to find whether there are some training samples for a given generated images, whether there are some training samples in the training data sets that is similar to this generated images, right? So if this score is high, then we have better generalization. We have less memorization. That is the mean of this generalization score here. Okay. Any questions for this score? If not, we go ahead. Then, so we further do the following experiment. That is, we plot a figure about the x-axis is the number of training samples, and y-axis is generalization score. You can see here, as the number of training samples increase, right, then the generalization score increase from 0 to 1 on different the UNet, the number of with different number of training, the different number of network parameters. It shows a similar behavior. There's a phase transition from the generalization equal the scheme, the generalization score is 0, and until the scheme that the generalization score is 1, is most 1. Yeah, and we also try other data sets. This experiment, this figure, is plotted on the Silverton data sets, and we also try like the syllable A, FHQ, and the AFHQ. These different data sets, we can observe the similar phase transition behavior from memorization scheme and to generalization scheme. And another interesting point is about the transition point, especially for the generalization, this region. You can see here, the number of samples we need to such that the generalization score is approximately 1, is about 2 is larger than the 2 to 30th power, right? Is about 8,000 number of training samples, 8,000. And based on all the results in the existing literature for diffusion model to learn the underlying data distribution, we need about like for this Silverton, like we say it's about 10 to 3,000 power, right? But this you can see here is, of course, is not the case in practice. Okay. Next, I will also discuss talk about some complementary result in the literature that they observe the similar behavior to us, but on different setting. This is recent the iClear. This result is based on the recent iClear best paper. this figure, let's focus on the first two rows. You can see here in the second row, this one, there are some images generated by trained diffusion models. Like we can see, we focus on n equals to 1. The images, this is image generated by diffusion model. Then we find the close image in the training data that you can see here. They are exactly the same. And we can observe the similar phenomenon for the number of images is less than 1,000. You can see here, number of training samples is 10. This is generated by diffusion model. This is closed image in the training data. Still almost same, right? For the training samples, 100, 1,000, right? But case is different when the number of training samples is larger than 10,000. You can see here, in the 10,000, the number, this is images generated by diffusion models, and this is closed one in the training data. They are different, and more obvious when the number of training sample is larger than 100,000. So here, this experiments demonstrated they also observe a very clear phase transition, right, from memorization to generalization. And they also, you go ahead.
So this work. So am I also right to say that they're also using cosine similarity as the notion of closeness of image?
No. They use other metric. They don't use
Okay.
they just directly compute the pixel, the difference between images, and then find the close one, instead of using the cosine similarity.
Okay. So
Yeah, you
that
can see
seems
here,
to be
right?
okay. That seems to be a bit of like some sort of Euclidean distance kind of. I guess
Yes,
I'm
yes,
not sure. Yeah.
yes, like
Then
that.
So my question is like there is this sort of Euclidean distance kind of measures, and then there's also like our perception. It means human eyes can tell if these images are the same, not the same. One thing I know is that, I mean, these two metrics, like in terms of cosine or Euclidean versus our human eyes, those are actually sort of different metrics. And is it legitimate to ask, like, even though like these images that you output here are the closest image in terms of the cosine or the Euclidean distance, it's not really the same as the human distance. Do you know what I mean?
Yeah,
Yeah. So I don't know.
maybe. Yeah,
I'm not
you
sure.
know.
Yeah.
I get your point. Yeah,
Yeah.
they may have some positive correlations, but sometimes maybe the metric, like the metric defined the like a generalization score or this here, they use it's not high, but maybe from our human, these two images are not close to each other, right?
Yeah. Yeah. I don't know. I don't
Yes,
know. Just
that
yeah.
is. It is. Sometimes it is.
Okay. Okay. Thanks.
Yeah. And then they further validated this observations. That is, they plot. We just focused on the yellow pixels here, the yellow lines. You can see here, they plot the distribution of cosine similarity. When the number of samples is very small, the cosine similarity of the generated images and the closed training samples always concentrate around 1. That means they are almost the same. But when the number of training samples increase, it shifts to like 0.75, right? As number of sample increase. That means they gradually become different, the generated samples and the closed training samples. Okay. Yeah, that is this results in the literature also validate our observations. So next, we will try to provide some theoretical understanding and also empirical validation on this two different regimes. We want to understand why diffusion model has this behavior. And first, we focus on the memorization regime. That is why diffusion model just generate the samples that already exist in the training data. That is big. Our answer is diffusion model only learn the empirical distribution in this regime when the number of samples is very small. That is learn this multi-delta distribution over the training samples. This one, yes. Why diffusion model just learn this empirical distribution? That is because in this case, when the number of training samples is small, like we just have 10 or 100 samples, but the neural network we use, like UNet or transformer, it contains of millions of parameters. is extremely large than the number of samples, right? This is typically the highly overfit case. Then in this case, we can treat the neural net, the training loss of diffusion models, the network, like an unconstant feature optimization variable. Just treat it as a free optimization variable that this S. And in this case, we can compute the closed form solution for this training loss. That is take this form. You can see here that is the like this one is softmax combination. The weight is softmax combination, right? Times the training samples minus this the xt. Yeah, this is the empirical optimal score function. So then we further validate the distance between this empirical optimal score function and the score learned by diffusion models trained on small number of training samples. Here we define a metric that is a reproducibility score. This one, actually, this score is to compute the similarity between to measure the similarity between these two different score functions, and here we realize the number of training samples against the RP score. This one, you can see as the number of training samples increase, right? This score gradually decrease. That means this empirical score is gradually different from the learned score by diffusion models trained on small number of training samples. In other words, when the number of samples is very small, this score is close to the trained diffusion models is very close to this empirical score. That is means diffusion models learn this empirical distribution. But when the number of trained samples is large, the learned distribution is not this one. And we also plot the training loss over the number of training samples. You can see here. When the number of samples is very small, it highly overfit the diffusion, this network, and the training loss is almost zero. But as the number of training samples increase, the training loss increase significantly, right? Okay, that is the memorization scheme. Then in the generalization scheme, the diffusion models, our answer is the diffusion model in this regime learns the underlying data distribution. However, this is not easy to validate this answer because for real-world data sets like MINDS, the CIFAR-10, right? This one, we cannot access the underlying distribution. So to validate our answer, we suppose that the underlying data distribution, we consider a very specific data distribution that is a mixture of low-rank Gaussians. We use this one to approximate the image data distribution. You can see here that is this one, the mixture of K Gaussians, and the mean 0, and the covariance is UK transpose, and this UK are some orthogonal matrix, and this is low, and this R is much lower than this D. The intrinsic dimension is much lower than the ambient dimension D. Well, then we use this diffusion models. We use this underlying data distribution to generate samples, and then train a diffusion model and get this learned score. Get this learned score. And then we also directly use this data distribution to compute the true score. And then compute the L2 distance between these two scores. And visualize and do some visualization. You can see here, as number of training samples, the x-axis is training sample. As number of training samples increase, these two scores, the distance gradually decrease, right? That means the number of samples increase. This learned score is getting closer and closer to this true score. This validates the conjecture about the generalization, what distribution diffusion model learn in the generalization regime, that is to learn the underlying data distribution. And recently, we also do some experiments on real-world data sets, but this is not in the asset. We consider distillation regime. We first pre-train a diffusion model. We haven't showed this. We haven't included this result in this slides, but I can talk about it a little bit. That is, we first pre-train a diffusion model on like ImageNet or Cipher10, this data set, right? We first pre-train a diffusion model, and then use this pre-trained diffusion model to generate some training samples, and then use this training samples generated by this pre-trained diffusion model. We train another diffusion model, like a teacher. This is teacher diffusion model, and then we train a student diffusion model. Then we increase like training samples, then compute the distance between the teacher and the student diffusion models. And this can validate. We can also observe the similar behavior for this, for diffusion models, for this in this generalization scheme. Okay, we go ahead. So in the previous section, we mainly expressed an intrinsic behavior about diffusion models, and also try to answer and figure out what diffusion models learn in different regions. And now a remaining question is about the generalization. Why diffusion model can generate new samples without suffering from the cross-dimensionality? We try to understand this use low-dimension modeling. In this part, we mainly focus on in previous section, the diffusion model, the training loss, we mainly focus on a neural network to learn the score function, right? And here we mainly focus on use a neural network to learn this post-mean, because according to the literature that is using the treatise formula, these two parameters, the post-mean, are equivalent in terms of equivalent to the score function up to this xt. Yeah, that means if we learn this post-mean well, right, we can also learn the score function well. Okay, so in the literature, they call this one the parameterized network to approximate this post-mean as the denoising autoencoder, this neural network. So then use this, we can further write the training loss to learn the score for the network parameters of this DAE as follows. The training loss, that is this one. This is essentially the empirical loss. We directly plug in the training samples xi into the training loss, right? Then get this one. We have a summation of the training samples and also the integration of the time, the training time. The time t, and the expectation of the noise. That is, we will mainly study later. We will mainly study this training loss. Okay, and next we will also give some model, some assumption on the underlying data distribution of the image data. We mainly explore the low-dimensional structures in the image data based on the following observations. The first one is there are some previous work like 4 and 5 years ago, PAP and there and the co-authors find the intrinsic dimension of image data like the MINDS, the Cipher10, and also the ImageNet, this standard data set, their intrinsic dimension is really, really low. Like you can see here, in their different tests, they found like the intrinsic dimension of ImageNet is just about 40 or less than 40. Compared to their ambient dimension, right? This intrinsic dimension is really low. And the second observation is based on the recent, last year, some recent work. They observed that actually this image data lies on a union of disjoint manifold. But this manifold is some nonlinear manifold. Like for Cipher10 dataset, different number of the images in different class lies on different nonlinear manifolds. Okay, and in our recent experiment, we also observed some low dimension structure in diffusion models that we plot the new memory rank, the ratio of new memory rank of the Jacobian of the denoising autoencoder. Essentially this one. We plot the new memory rank of this one, this parameter, and against the signal to noise ratio. Against that is a different time the added noise. Then we found when the close to the image, the intrinsic, the numerical rank of the Jacobian of denoising autoencoder is very low. The y-axis you can see here is rank over the total dimension. It's very low, right? And this means the denoising autoencoder of trained diffusion model, the rank is very low. And these three observations motivate us to model the underlying data distribution for like image data as a mixture of low-rank Gaussians. Of course, we have to say this model simplify just the approximation and the underlying data distribution of image data, of real-world image data. And it's also not so realistic, I have to say. In this model, we model the data distribution of a mixture of k low-rank Gaussians. And for each Gaussian, the mean we model at 0, and the covariance is UK transpose. And UK transpose, and this UK are low-rank matrix. The DK is usually significantly less than N. Well, actually, this 0, this is as long as the mean is known, you can replace this 0 by the given mean, like mu k or other, just is given. We can replace it by the not just 0. And actually, there are some existing work. They use other mixture of Gaussian models to model the underlying data distribution. Like in recent work, they model the data distribution as a mixture of k full-rank Gaussian. What they in their model, they want to estimate this mu k star, and the covariance is given. The covariance is given at the identity. Like different from our model. In our model, we suppose this mean is given, that is 0, but the covariance is unknown. We need to estimate it. Obviously, these two models are very different, right? Since our model, just like if we sample some data from this distribution, that is like this data may lies on a union of linear subspace, right? Linear subspace. But in this model, the data lies on a full-dimensional space, right? With different clusters. This is difference between these two models. Any questions? Okay. If not, we go ahead. So based on this model, we can further to compute the poster mean based on this model. Actually, the form is very simple. Just the projection of data points on different subspace with the weight combination, and this weight is determined by this form. Okay, and then based on this, the poster mean form, we can further parameterize the denoising autoencoder into this form. You can see the only difference here from this equation, this parameterization, right? Different from this means this UK now is unknown, and we need to estimate it. In here, the UK star is just what we given in the model, right? And then we consider the parameterization, and we need to estimate this UK. And under this parameterization, learning the post mean or learn the score function is the amount to learning the to learn this basis matrix UK. Okay. Next, we will do some theoretical analysis. That is, first we consider we just have one low-rank Gaussians. We generate some samples based on this distribution, right? We just had one low-rank Gaussian, and then generate samples use the one Gaussian. The low-rank Gaussian, and plug some noise. And based on the previous parameterization, right? If we just set capital K to 1. Then we can get this parameterization, and then we plug in this parameterization in the training loss before, into this training loss, into this one. In this training loss, we can show that actually this training diffusion model training loss is equivalent to this PCA problem. It's very simple. We can get very simple, the equivalent form. And then use this model, we can further show phase transition in optimality. That is, with high probability, when the number of training samples is larger than the intrinsic dimension D, the optimal solution of the training loss of diffusion models can recover the underlying basis, the true basis, up to some noise, the controlled by the noise, the magnitude of noise. And otherwise, if the number of samples is small, less than intrinsic dimension, we cannot. And this reviews a phase transition of success, from failure to success of diffusion models when learning the underlying data distribution. And in some sense, this explains why diffusion model can learn the underlying data distribution without suffering from curse dimensionality. Okay, and then we consider a mixture of K-rank Gaussians. We can use a similar setup and plug in the optimal parameterization into training loss and show the equivalence of diffusion model. The training loss is equivalent to subspace classroom problem. It's like a generalization of PCA problem and show the similar phase transition of training samples as long as it's larger than the linear, the intrinsic dimension for each subspace, we can learn the online basis. Well, and we further validated this result in using some experiments. First, we only have one subspace, we can directly show there's phase transition for PCA problem, right? You can see that this is number of training samples, x-axis, the y-axis is the intrinsic dimension. There's phase transition from the failure. The dark pixel denotes the cannot. The white pixel shows its success. This phase transition, right? And then we train a diffusion model. We use a stochastic gradient descent to train diffusion model, and then get a similar phase transition. Of course, since we use stochastic gradient descent, right? Sometimes we may fail to recover at the boundary, and similar behavior we can observe for multiple subspaces. So then we can use some theory to do some controller generation, and this part actually is very. I'll just make a few slides, and it's very simple. This just is mainly based on our following observations. That is, there is a correspondence between the single vectors of the Jacobian of denoising autoencoder and the semantic image semantics. Like you can see here, for this images. In a trained diffusion model, we found the leading single vectors of denoise autoencoder correspond to the gender of images. Like you can see here, if we increase at some xt, we take a step along this direction, the generated image gradually become the women, right? And then in this direction, the negative direction become the man. And other single vectors correspond to other semantics, like the head, figure, and the color, this different semantics. Okay, so based on this semantics, the correspondence between the single vectors and the single vectors and the semantics, we can further design a low-rank controllable image editing method. And in our experiment, we found that the method is very precise and disentangled to do the local image editing. And especially, we don't need to pre-train the diffusion model. We can apply this approach to the pre-trained diffusion model. And just do some editing. Yeah. So I think the time is up, right? Okay. We draw some conclusions based on our this empirical, some theoretical and also empirical studies. First is in this work, we mainly try to understand distribution learning of diffusion model. First, we show intrinsic behavior, that is memorization to generalization regimes. And we also want provide understanding, that is why diffusion model exhibit memorization and generalization regime, right? And also try to understand why diffusion model learn the underlying data distribution without curse dimensionality. And finally, we use correspondence between the semantics and the basis of Jacobian. We can design a training-free method for image editing. And finally, recently we also consider extend our current analysis, because in our previous analysis, we impose some strong conditions, like the latent variable for mixture of low-rank Gaussian, right? It's Gaussian. Can we extend it, relax it to sub-Gaussian? And also in our analysis, we just consider optimal parameterization, but in practice, we usually use all parameterized network. And can we do a dynamic analysis to show diffusion model can learn the data distribution in all parameterized network, and also like use low dimensional structures to improve the sampling efficiency analysis. Since in this work, we mainly focus on the learning dynamic analysis. And the second main direction is about extend our current analysis and also experiments to large language models. Since in large models, there are also some work observed like phase transition from memorization to generalization, right? And can we also design a theory-guided approach to interpret and improve the practice of the large language models? And many other open questions like about model safety and privacy and also robustness. Well, that's all my talk. And any questions? Thank you.
Thank you very much. Floor is open. Questions?
Maybe I can start. So can you go back to the slide on the image editing?
Yes.
So my question is basically that you have these interpretations of the different dimensions. Is this something that you get a posteriori? You need to look at the images afterwards and fiddle around with these parameters and see what happens, or is this something that you can and if you do it, then like engineer?
Yeah, you're right. This is engineer thing. Like, we compute the first leading single vectors, right? And then we actually we have some I have some supplementary slides to demonstrate what we do here. Sorry, it should be here. Like we take at some xt, we take a step along this we want these directions, right? And then use it to generate the figures. Like you can see here, generate some. You can see with different alpha, this controlling strength, we generate the different figures, right? And then figure out the correspondence. Like this one, we want corresponds to this gender, and other similar, yeah.
Okay, and you look at many images and kind of draw conclusions.
Yes.
Yeah, but
Yeah.
you couldn't before. If I want to be able to add a hat, you would not be able to kind of engineer the method to make that happen in one of the dimensions.
Yes.
Okay. Yes.
Yeah, we first need to figure out the correspondence, and then we can use this correspondence
Yes.
editing. Yes.
Thank you.
Yeah. There's an audience has question, right? Go ahead.
Yes.
Yes. Hello. Can you hear me?
Yes, it's good.
Yeah, sure. Okay. No, on that same slide, there are similar comments. I don't know if you have read the literature about diffusion maps. In a similar way, when we do the again decomposition, you can see it may have some semantics, in the distribution of the images. You should look at that. I think there might be some relationship. Diffusion maps, maps and diffusion maps. People used this before.
Oh, you mean eigenface, the
Eigenfaces, yeah, sure.
Yeah, that well, yeah, it is. I think, but that correspondence maybe just in terms of human face, but in our experiment we have some more extensive result, like on other even on other data sets. We can like docs,
Okay.
right? And also some architecture. You can check our SML the recent newspaper. We have extensive results on this on different data sets, not just the human face. This one, the third one, of the exploring low-dimensional subspace in diffusion models for controllable image editing. Yeah, we have extensive results.
Yes. I know for instance, eigenmaps or eigenfaces is we're mostly looking at faces. I'm just curious, probably it might also work if you apply it to these other situations. But I have another question. My question was in the calculation of your generalizability score, you have this threshold 0.6 popping up. Why is that? How did you decide that you should use 0.6?
Yeah, great question. I think the main reason is because when we computed this, right? And we found when this number take at 0.6, and these two images is very close. You know what I mean? Like
This is something like a
we
tuning.
visualize it. We human visualize it. Yeah.
Okay.
Yeah, it's larger than that. And second is we found even you use other like 0.7 or more strict, you can observe the similar behavior. That is face transition. But the transition, this part may shift a little bit.
I see.
Because you use like a strict criteria.
Interesting.
Yeah, thank
And
you.
one last question, if I may. Going back to the slide before this one, I was looking at how you compute this score. Just one more slide before this.
Oh,
Can
one
you
more
go
slide.
back?
You
Yeah.
mean this one?
Before.
Before.
Where you're computing the generalization score.
Oh, I compute generalization. Let me think. Here, right? Or which one? This is 17.
So where I was talking about the 0.6 threshold, that
one. Okay. I see. This one,
yeah.
right? Okay.
Here, yes. In the diagram above, you have two. So you're comparing two images, X1 and X2. You add the same noise, but you put them through two different diffusion models. Do you think this has any impact? If I were to use the same diffusion model, probably I would have done that if I were to do this to see if the images are close or not. Why do you have to use a different diffusion model?
Good question. Yeah. Here we just here to in I should clarify. Define this metric. You just need to focus on this part. Just on this part.
Okay.
This why we use two diffusion model, because that is in our another work we study phase transition. The reproducibility, that phenomenon, that is train different diffusion models on same dataset, and then use the same noise to generate two images, like X1 and X2, right? And then we found their similarity is almost one. They are very, very similar to each other.
I see.
Yeah. That is about another, but I directly use that figure here. I should remove this. Yeah, I should remove this part. Yeah.
Okay, no
Thank
problem.
you.
Thank you. Yeah.
Are there any more questions from the audience?
Yes.
Okay. All right. I think I don't hear anything, so I think I'll stop here. I think there's still a lot of, I'm not sure if anybody have any more unofficial questions. If not, I think I'll stop the official segment. We can stop the recording.